Hello, this is Concrete Pat, and today's lecture is about the problems of the torsion of circular shafts. Let's go get those shafts. Let's go. So first one is that you have a statically indeterminate structure that you say shaft. Then you apply the torque T at A from A and B from B, and you need to say what is the value of torque developed at A and torque developed at B. Twisting moment developed at A and twisting moment developed at B. So if we solve this one, if we make a line diagram, I would say that the moment is applied anti-clockwise direction. So your right hand thumb rule, right hand should be applied. You rotate your right hand in the anti-clockwise manner. So you rotate your right hand in the anti-clockwise manner. Then the then the thumb points towards the point support B. That's the direction is in this way. Direction is in this way. So you rotate your thumb in this way. So we got this. We can call it as T, and we have that. We say that this one is going to resistate. Let's say this is some TA, and this one is also resistate. So let's say this is TB, and we can write TA plus TB equals to T. And one more thing is that we have the compatibility. We have the compatibility condition, compatibility equation that the theta at A is equals to theta at B, that equals to theta B with respect to A, that is equals to theta A with respect to B, that equals to 0. And let's call this point as C. Let's call it this point as C. We can say theta B with respect to C plus theta C. Yeah, theta B with respect to C plus theta C with respect to A, that would be equals to 0. Now we need to have those forces in the both those sections of AC and BC. Now, if you take that section, I would say, if you make free body diagram, I would say this is your some value of T, TA, and here there would be some value of TA. But after that, you just cut right, just left of that T, just left of that C. So after that, there would be TA also here, and you are applying a value of one more T there. So net value, we can say that would be T minus TA, that equals to TB. So that got satisfied that TB equals to T minus TA. That's also satisfied, T minus TA. Now we got that one is your that we can say one is your negative, next one is your positive. So if you make the TMD, I would say you are going in the direction, in this direction, your traverse is in this direction. So but you are facing TA is in the opposite direction. TA is in the opposite direction. So I have to make that negative TA, minus times negative TA. I would go that. So then after that, straight, and you are facing now a TA, that T that's in the same direction. So you have to increase it. You have to increase it, say, by some value such that it becomes equal to T minus TA, T minus TA. Then after that, it's constant. After that, you are facing TB in the opposite direction, so it goes down by amount of TB that finally equals to T minus TA. So you got the TMD diagram. You got the TMD. Now you can say theta total will be equals to 0. So you have this length of A and you have this length of B. I will write theta B with respect to C. So that equals to this part is your part B, C, A. I would write theta BC equals to T. What is the value of T for here? That is T minus TA. Your torque of T minus TA, length of B, and GJ. You got this one? One more thing, yeah. So we have already, I think we have already solved this problem. All right, let's solve it further. Let's solve it further. So we got this one. And similarly, from the other side, we write plus theta CA. So you have negative TA. Then length of A by GJ, that should be equals to 0. So you got the value that TB minus TAB minus TAA equals to 0. That means TA A plus B equals to T times B. That means TA equals to T B by L, or we can say TA plus B. So you got this value. Similarly, you can say T B equals to TA by A plus B. So let's take the similar problem. Let's take the similar problem on this one. Now the cross section is varying. Now the cross section is varying. So you have L1, G1, J1. After that, you are having now L2, J2, G2. Okay, okay, you got this. No. You need to say this is A, this is B, this is C. You want to say what is the value of TA and what is the value of TB. So let's have that similar fashion. Now you are applying the torque at the junction. You're applying the torque that's anti-clockwise torque of T. I would say this is your line diagram that TA rotate your right hand anti-clockwise. That means thumb points toward the support B. That's in this way. That's your T. That means here would be some resistance of TA opposite. Similarly, here would be some TB. Similarly, we got TA equals to we can say TB equals to T minus TA. So one more is that compatibility condition that theta b equals to theta A equals to 0. That is theta b with respect to A, that is also 0. That is theta b with respect to C plus theta C with respect to A, that's also 0. So now let's go for those let's go for the TMD. So we have this value of TA, then after that it would go upwards, T minus TA. So this was your BMD or TMD. So you got this one, negative, positive, negative, positive. Now write the equation. So you have this length of L1 and you have this length of L2, and G and J is also different. So let's write the equation theta BC, ABC. Write the equation theta BC. So I would write T minus TA L2 by G2 J2 plus your torque, second one, that for the AB you have minus TA L1 by G1 J1, and that equals to 0, that equals to 0, that equals to 0. So you got this. You got the value that T by G2 J2, that should be equals to TA. That should be equals to TA. TA you can keep common as it's TA. Then you have L1 plus L2, L1 plus L2. Yeah, L1 by J2 J1, and you're having this one, and you're having this one also, that G1 J1, is it same? G2 J2, G2 J2. Yeah, you got this. Actually it should be you got this L2 by G2 J2, G2 J2, G2 J2. Then after that you had L1 G1 J1, L1 G1 J1. So you got this one, and you can get the value of TA now. Let's go for the value of TA. That would be equals to T times, and you got this one. So the value for this one would be equals to that would be equals to G2 J2 L1 plus G1 J1 L2 by divided by J1 J1 G1 J1 G2 J2, and you reverse it, and you would get a value of G1 J1 G2 J2 divided by G2 J2 L1 plus G1 J1 L2. Yeah, you have already there that T times L2. You already have that T times L2. So you write T times L2. So finally you got some value of that T L2, and this part can go G2 J2. So you got J1 G1 J1 by summation of Li Gi. Oh no, it should be in this way: L1 G2 J2 plus L2 G1 J1. you got this, you got this, you got this, you got this. That the torque, this was your T minus TA for the length of L2, G2, J2, and minus TA, L1, G1, J1. Yeah. Then after that you did T times L2, G2, J2. That after that you have this TA, then you have L1 by G1, J1. Similarly, you have L2 by G2, J2. Yeah, everything is perfect. So you can solve this part. You can get G2, J2, L1, G2, J2, L1 plus G1, J1, L2 divided by G1, J1, G2, J2. Then you, from this side, you have this part, and you can write T minus DL2. Yeah, everything is okay. Everything is okay. So you got this. You got this. Everything is okay. So you got the value of TA equals to TL2 J1 G1 divided by summation of L1 G2 J2 L2 G1 J1. So for if you take for G1 equals to G2 equals to G, then you would get value of T equals to TL2 G J1 divided by L1 J2 plus L2 J1, and G would get cancelled, so you would get this equation TL2 J1 L1 J2 plus L2 J1. And similarly, you can get the value for the T2 also, TB also. You can get the value for TB also. You can get the value of TB also. TB would be equals to T times L1 G2 J2 divided by L1 G2 J2 plus L2 G1 J2 J1. So you can get this equation. So let's have the one more problem. So let's have the one more problem. Let's take one more problem. So you got this. You got the shaft. You got some shaft. That, let's say this is some shaft of length. Your diameter of the shaft is 300 millimeter, and your permissible angle of twist permissible equals to, that should be equals to 1.5 degrees. This is your permissible twist, angle of torque. Okay, and your permissible shear stress is also equals to, that's also equals to 42 megapascal. Your value of modulus of rigidity is equals to 84.4 gigapascal. And one more thing is that you have a length of L equals to 7.5 meter for the shaft, and you need to say what's the maximum torque you can apply. How much torque you can apply on this shaft of length L equals to 7.5 for these set of conditions. What is the maximum torque you can apply such that it would not fail in shear? So let's say we have that equation, that torsion formula, tau by r, T by j, and g theta by L. And from the conditions you can see you have theta given, you have tau given, and you have g given, but t is not given. So if I solve for this part first, I would get some value of tau. If I set the, let's say, if I set the value that tau by r equals to g theta by L, and if I write what should be the value of tau at the rate of theta permissible, because you can't go for tau max if the theta is more than theta permissible. You have to see on which shear stress your theta would reach, theta permissible would reach. Would say on what theta you are permissible, on what shear stress your theta goes to theta permissible. So let's take that, let's write that. So you got some value of theta, yeah, that tau equals to g theta by L. G was your equals to 84.4 gigapascal, 84.4, that becomes megapascal, and your theta value of 1.5 degrees, and you convert it into radians. into pi radian, I would say. Let's forget the radian. You got this value. After that you have that value of r. The value of r would be equals to r max. The value of r would be r max. You can go for r max. That would be radius. That would be diameter by 2. So your diameter of 300, that means this part would become 150 millimeter. And you got this length of L. You divide the entire thing by the length of L. You divide by the length of L. The length of L equals to 7500 millimeter. So you got a value of that tau. It would be equals to the tau that can be allowed. I would write tau allowed. How much tau you can allow? That would be equals to 44.2 megapascal. So this is your, that means we can say that shear stress developed at the rate of permissible angle of twist. At the rate of this theta, you got a shear stress value of 44.2 megapascal. And if you want to say what is the value of torque maximum, how much the maximum torque you can apply, by the relation you can say that shear stress should be maximum. R should be that R would be some value of R max, I would say. And one more thing is that J. So your tau maximum would be at. So you need to say tau should be maximum, but you need that tau max, that T max, at the rate of safe shear stress. You should resist the torque safely. That means tau should be less than the tau permissible. So you can't say I can keep the tau as maximum. You should go for the permissible shear stress from the question that you have, from the conditions you are given in the problem, that if you see this tau permissible equals 42 megapascal, and you got that tau can develop 44.2. That means if you are allowing that theta equals to 1.5 degrees, that means your shaft would fail. Your shaft would fail at this shear stress. So you need to keep the shear stress below that value. That means you need to keep shear stress of 42 megapascal. Shear stress of 42 megapascal. And if you substitute that value of shear stress equals to 42 megapascal, that means maximum torque you can apply that is when that tau is permissible value. Tau is permissible. So we can write tau is with your tau permissible 42 megapascal. And you write d by 2, that is 300 by 2 millimeter. Then divided by j, that's pi by 64, and 300 power 4 millimeter power 4. And you got some shear value of torque, maximum torque you can apply. That would be equals to 222.6 kilonewton meter. You got this value. And one more thing is that you can do it in the reverse manner also. If you take, let's say you take that I want theta twist to be maximum. If I take in this way, that I go for the tau max initially. If I go for the tau max, that I can keep as 42 megapascal, and I write tau max by r. R would be 300 by 2. If I write in this way, tau by r equals to g theta by l, and I would write theta, some value of theta I don't know, g theta by length of 7500. So I can get the value of theta, how much theta I can keep. If the theta, you got some value of theta, and you substitute that value of theta here, and you compare the two values of theta. The lesser one of that out of those two theta, let's say you got some value of theta equals to a, and from this side you got some value of theta equals to 1.5. You see which one is your lesser, and you substitute that one in the equation, that t by j equals to g theta by l, g theta lesser by l. So you can get the value of t max. Let's take another problem. You have a bar, you have this bar phi of the bar, diameter of the bar is 40 millimeter, solid circular cross section, solid, and at a distance of 1.2 from one of the sides, I would install a bracket. Install a bracket. So I would then apply a load. So the bracket is in the z direction. So I am applying a load in the y direction. Py equals to some value of 25 kg. That would be equals to 250 Newton. So I am applying a load of 250 Newton. So the distance of the load from the center, that equals to 0.5 meter. And because of that, you need to say what should be the maximum tensile stresses. What is the maximum tensile stresses in the bar? What is the maximum tensile stresses that have developed in the bar? So because of this, you would say your couple, or we can say your loading is out of the plane. So that's perpendicular to the polar axis. So a moment of moment would be developed, or torque would be developed about the polar axis. So your torque developed would be equals to that Py into some value of that eccentricity of that load. I would write that would be equals to 250 Newton into 0.5 meter. So your value of 125 Newton meter torque applied clockwise. So you got this value of torque. Now one more thing is that if you transfer this force, if you take the free body diagram of this bracket, you are applying a load of P here, and same would be resisted at this point on the bar. That I would say that this is also P, and a moment developed in the bar, in the bracket. So in the bracket you have developed a moment, bending moment. In the bar you have developed a bending moment. That's equals to P into E. Then after that, same would get transferred to the bar, to your shaft, to your main bar or main shaft. So this is your main shaft, and you are applying a load of P downwards, and a moment that was in this one, it was anti-clockwise. Here it would be clockwise. So your clockwise moment. How to show clockwise? Clockwise in this way. Yeah. So it's a clockwise moment that is in this way. Clockwise moment. Yeah, clockwise should be in this way. Clockwise moment. This is your clockwise moment in this way. Clockwise moment developed equals to 125 Newton meter, and your load was equals to 250 Newton. Now, based on this, you are having two loads. One is your bending moment, one is your shear force, one is your transverse load, and next one is your torsion moment. So I would say this is your length of 1.2 meter, and this is also 1.2 meter, and your sides are supported by those fixed supports. I would say this is your beam now, and you can separately solve for transverse loading, and next one is your twisting moment. Let's calculate for the twisting moment. I would say a moment clockwise, that means thumb points towards the support A. So this is your support A. That means thumb points towards the support A. I would say this is your value of 125 Newton meter. And by the symmetry, can you say this would be 62.5, and this also would be 62.5. This would be also 62.5. Can I say? If I make the diagram TMD, I would say 62.5. After that, there is decrease. Similarly, there is 62.5. Torsion moment diagram. So you got the maximum torque twisting moment in the section. You got the twisting moment maximum. That is same from both the sections. Let's take this twisting moment for now to side. We need to get the maximum tensile stresses. Now, if you talk about that we call as, if you talk about those Normal stresses, we have normal stresses equals to my by I. So you can get the normal stresses from the bending moment diagram. If you make the bending moment diagram for this term, you are applying a load, of P at a distance of L by 2, and supports are fixed. So the bending moment diagram looks like a linear variation. It looks like a linear variation. That PL by 8 at each of the corners, PL by 8, and PL by 8. And this is your negative, positive, negative. So the value of P here would be equals to 250 Newton. 250 Newton into length of 2.4 meter and divided by 8, that equals to 75 Newton meter. 75 Newton meter. And you got this value of M. Can you say what is the value of bending stress? Can you solve for the value of bending stress? Can you solve for the value of bending stress? What is the value of bending stress? Sigma, that equals to 75 Newton meter. M, Y. The value of Y would be equals to diameter by 2. If you have this cross section, and the variation of bending stresses is in this fashion. Value of bending stresses, that equals to, that's maximum at the top and bottom fibers. That equals to my by I. That is sigma bending. So we have this one. If you take their diameter, that Y max would be equals to diameter by 2. So diameter of 40, that means 20. So you write 20 millimeter divided by I neutral axis. What is the value of I neutral axis? That's pi by 64 d to the power 4. Pi by 64 d to the power 4. Pi by 64 d to the power 4. Millimeter power 4. You got the bending stress value equals to some value of bending stress that equals to bending stress value equals to 11.942 megapascal. 11.942 megapascal. Now, similarly, if you take the torsion, that because of the torsion you have twisting, you have the shear stress tau max. What is that value of tau max? Because of torsion, that equals to TR by J. If you directly write that tau by R equals to T by J, value of J for the circular shaft, that is pi d to power 4 by 32. That's polar moment of inertia, and value of R would be equals to d by 2. So you got a value of 16t by pi d cube tau max. You can directly remember this one now. 16t upon pi d cube, 16, and the t value should be maximum. Out of these two, we have to take maximum value. So maximum value would be equals to 62.5 Newton meter. 16t upon pi d cube. So value of d is your 40, and you can get the value of tau max would be equals to, tau max comes out to be equals to 4.976 megapascal. Now you got the bending. If you know the variation of bending stress, do you know the variation of the shear stress? You had the circular shaft, and there is some resisting torque, and we know that the direction of shear stress is maximum at the direction is in the same direction of that or torque that's tangential to the surface. So we know the variation, shear stress variation, that's in this way. That's also linear variation. And I would say if you take any point on the corner, let's say this is point A, this is point B. So the critical condition for the you need to get the maximum tensile stresses. That's indirectly saying get the major principal stress. Because of the combined loading we can get the major principal stresses. So we can have a general loading of that. We would have some tau. We would have some value of tau, and we also have some value of stress, bending stress. So if you take any particular point, if you take A and B, I would say there is some bending stress equals to we already calculated that. See where was the figure. So this was your bending stress. I would say on this point A and on this point B, we have some bending stress. One is your negative, positive. So we have the bending stresses, maximum bending stresses. And if you take any other point, we have lesser bending stresses. If you take this point, we have lesser bending stress. We have zero bending stresses here. So if you take C and D, we have lesser bending stresses. But by the shear stress variation, see from the shear stress variation, it is maximum at every that means it's maximum on the surface. If you take any section, if you take this point and this point, there is also maximum. This is EF. There is also maximum shear stresses. That is in this way. We have the shear stress variation. It is also maximum. That means tau maximum because of torque or torsion. That's maximum at the surface. That's maximum at the surface. At every point on the surface, you have tau max. You have tau max. But for the bending case, you have the case for that sigma is maximum at the 2 points only, at these 2 points A and B. If you take this element, we have bending stress equals to 0. And one more thing is that if now third one is that third top part of the, because loading is transverse, we also have shear force. So we can have direct shear stress also. So we have the variation of direct shear stress in this way. So now the thing is that you have different combinations of those. To calculate the principal stress, we have the equation that sigma major equals to sigma x plus sigma y by 2 plus minus sigma x minus sigma y by 2 whole square plus tau xy whole square. And one more thing is that, see, you have one of those sigma equals to 0. One of those sigma you can take 0. And similarly, one of those sigma you can take 0. And value of tau would be, you can take the combination of tau. So you have different possibilities of that sigma. If you take different points, and you can then compare the values. If you take point A, if you take sigma principal stresses at A, that equals to, I would write, at this point there is some tau because of torsion. There is some tau, and there is some tau because of direct shear stress. That is 0. Because variation is in this way. So here the shear stress is 0, and in this one here you have tau max here. And if you take bending stresses, that's maximum at this point. So that we have maximum bending stress at the point A. Now you have this combination 1. Now second combination is that if you take this point that you call as C point, if you take point C and write major principal stresses at the point C, I would say the stresses here would be equals to, this is point, because of the transverse loading, I would say because of the transverse shear force, that tau would be equals to maximum. That is tau max because of direct shear stresses. And because of torsion, we also have some value of tau. We can have some value of tau because of torsion. So this is your tau max. This is your tau max for the point C. So we have tau max at the C also because of torsion. But if you take the point C, that's on the neutral axis. I would say. So the bending stresses would be 0. So sigma B equals to 0. Bending stress is equals to 0. Your bending stresses at point C equals to 0. So you got this combination also. But based on the values you got, if you see the values, if you see those values, you would say this value is 4.976, and your bending stress value is more. And similarly, if you take the shear stresses also, if you take the direct shear stress also, that would be lesser than the torsional shear stresses, because you are applying torque, and because of torque also you got some value of 4.976, and that sigma is very less. Sigma bending was some 12 value, 11.4976. So you got this value, bending stress is more. So if you want to take any point, that would be point A. That would be some point A or some point B. You can't take point C because your sigma is 0 here. No doubt there is some direct shear stress, but that value of shear stress would be some value of 1 or some value of 2 megapascal, and that you can ignore. With respect to bending stresses. So if you take point A, if you calculate for the point A, let's calculate for the point A that what is the normal stress that you can have. So I can directly, by intuition I can say that sigma would be maximum at A. That would be major principal stress, that is equals to sigma 1 equals to your sigma x. I can say this is your sigma x. So if you had the general state, I would say this is your sigma bending, and there is some shear stress. Tau. tau because of torsion, on the point A. You have this point A. So you can write that sigma bending equals to 11.942 plus 0 divided by 2 wholes plus 2. Then plus after that you have that radius 11.942 minus 0, 11.492 minus 0 by 2 whole square plus some value of tau. The value of tau here would be tau because of that torsion, that is 4.976 whole square. So you got some value of bending stress maximum that equals to 13.744 megapascal. So this is your major principal stress, or that is maximum tensile stress. Maximum tensile stress that has developed because of that given loading. So do you understand the problem? Do you got the problem? Do you got this problem now? Let's take one more. Let's take one more problem. So you have the shaft. You have some shaft and that cross section of some shaft. You have some part of the shaft. Let's say this is some part of the shaft. And one more thing is that on this side we have some load of P, and there is some value of T also. There is some value of T equals to 20 Newton meter, and a value of P equals to 250 Newton. The length between those 2 points is equals to 25 millimeter, and this part is your 75 millimeter. And there is some point somewhere here. That is a section. Let's say this is your AB section. Let's call it as a AB section. And you want to say what is the maximum shear stresses developed? What is the maximum shear stress developed because of applied forces and moments? So you want to say on this plane, I would say on this section, tau max on AB section, on your AB section, what is the maximum shear stresses developed because of those loadings? Now you have this 25, and after that you have this 75. Let's forget this part. We don't worry about this part. Our concern is that this section of that AB. And if you got this section, you should have this balanced section from the free body diagram. So let's say from this side it's also continuous, and from this side it's also continuous, and you are worried about this part AB. So let's have the free body diagram for the AB. If you say this is point, this is AB point, I am applying a load of here, load of 250, and there is torque also, T equals to 20 Newton meter. So I would say there should be some resisting torque here. This was your clockwise. Here should be some anti-clockwise 250. Yeah, 20 Newton meter. So you got some value of T resisting. And after that, you're applying a load of P upwards. And here there should be some shear force of 250 Newton downwards. And because of this load P, you can have that bending moment. You can have that moment about this point AB, and so you can resist some moment of there will be developed a moment of P into 0.1, because total length is 0.1 meter or 100 mm. So you can write a moment developed would be equals to P into 0.1. So I can show that moment also. So a moment developed in the anti-clockwise direction. To resist that effect of that 250 into length L, I would write that moment developed would be equals to 250 into 100 millimeter. So I would write 250 Newton into 100 millimeter. That is moment developed, resisting moment. So you got this loading on the, so now the cross section, you have this cross section. This is your ZZ, this is your YY, and your moment in the ZZ direction. This is your moment in the Z direction. So a moment developed in the Z direction, that's MZ, and your moment perpendicular to that's torque perpendicular to the plane, that's mx, that's also torsion, a torque, resisting torque of 20 Newton meter, and a shear force in the y direction, and a shear force of py in the direction of that y to 50 Newton. So you have three different loadings, and because of that, you have to say you need to get the value of tau max on the AB section. So you have this AB section. So you have this section, and there are 4 critical points: A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Okay. Now, if you say that I'm going for point A, if you are going for point A, because there are also some possibilities of different possibilities. If you take, you need tau max, you have different possibilities. One is that if you take tau at A, if you take point A, let's take point A. So you are applying bending moment, so there would be some bending stresses. There would be some bending stresses at the top and bottom. That's my by I. Okay, so you got some bending stresses here. And if you take the direct shear stresses, you can have direct shear stress, that is 0 here. So 0 direct shear stress, tau direct. And if you take those indirect shear stress because of torsion, I would say that would be some value of tau max. I would write tau max equals to TR by J. Yeah, or we can say 16T by pi d cube. So we have the stresses, we have some value of shear stresses and normal stresses on that top. Now if you write that equation, tau max equals to sigma x minus sigma y by 2. So I write sigma, let's call it as sigma bending. So I write sigma bending minus 0 by 2 whole square plus some value of tau max, tau t, let's call it a tau torque whole square. So I got some value of tau. I got some value of tau max for the point A. And similarly for the point O, for the point C, if you take point C, let's take point C. So on the point C, you have, this is on the neutral axis. So bending stresses, so sigma bending equals to 0. And if you take direct shear stress, I would say direct shear stress is maximum on the point C. So point C, direct shear stress is maximum. That's having some equation of, that the maximum shear stress is, that is equal to tau by 4 by 3 tau average. That's the equation we have, that 4 by 3 V by A 1 minus y square by r square. We have derived this equation. And you substitute the value of y equals to 0. That means the point on the neutral axis. So we say that the value of y would be, the tau max would be equals to, tau direct maximum would be equals to 4 by 3 tau average. And after that, if you take the shear stresses developed because of torsion, that is in this fashion. So this was for the plane AB. And if you take plane CD, if you take this section, if you take this line CD, and here there is also some bending that tau max. So we have this tau max, tau because of torsion. That's also max. That's T R by J 16T by pi d cube. So we have bending stress 0. So I can write now. So tau max here would be equals to, that's equals to 0 minus 0 by 2 whole square plus summation of those tau d plus tau t whole square. So I got the summation of those. I want to see which one of these is the maximum value. So let's take the point A. Now you have applied a bending moment of m equals to 250 into 100. That would be 25 Newton meter. That is 25 Newton meter. That's 25 Newton meter. 25 Newton meter, yeah. So a bending moment of 25 Newton meter. You solve it. You have this 25 Newton meter. So sigma bending equals to 25 Newton meter, and y maximum would be equals to the diameter. Let's say the diameter of the shaft. Equals to 20 millimeter. Diameter of the shaft equals to 20 millimeter. 10 mm. Is it 10 mm or 20 mm? I think 10 mm. Diameter of the shaft is 10 mm. This is 10 mm, 10 millimeter. So that means your y maximum would be equals to 5 millimeter. That means y maximum equals to 5 millimeter divided by I. The value of I would be equals to pi by 64 d to the power 4. And you got a bending stress value of sigma bending equals to 254.6479 megapascal. 254.6479 megapascal. That is very much. That's a huge shares that bending stress because the question says that the steel here is high strength structural steel, high strength steel, so it can take more stresses, it can take more tensile stresses and more shear stress. So highest tensile strength steel. So we got the bending stress value, that 254.6 megapascal. Now you want to say what is the value of that tau max because of torsion. That is TR by J, so that is 16, and the torque value would be equals to the torsion you applied, that was equals to 20 Newton meter, 20 Newton meter, 20 Newton meter, 20 Newton meter divided by pi and d cube. So you got some value of that direct shear, that direct torsion, that is equals to 102 megapascal. That torsion, because of torsion, that shear stress tau t. So 102 megapascal. Now if you say what is this value, and one more thing is that direct shear stress 4 by 3 tau average, tau max because of direct shear stress, that equals to 4 by 3. The value of tau would be equals to v by a, and shear force equals to 250 Newton by area, pi by 4, 10 square millimeter square. So you got some value of shear stress, that is direct shear stress equals to 4.24 megapascal, 4.24 megapascal, 4.24 megapascal, 4.24 megapascal. Now let's solve for the first part, that is tau max C. If you calculate what is the shear stress maximum on the point C, I would say that equals to, that is 4.24 plus, and second one was your 102 megapascal, 102 megapascal because of torsion. So you got some value of that. That's 106. That's 106.24 megapascal. So you got one value of tau max. And next one is that if you take point A, here we have a bending stress value of, what was the value of bending stress? Bending stress comes out to be equals to 254.67, 254.6479 divided by 2 whole square plus, and tau t 102. Clearly we can say that shear stress is at A, that's more. Shear stress is developed at A, that's very much. So I would say that equals to 163 megapascal. And I would say this value is equals to tau max in plane. This is your maximum stresses in plane. So tau at A is maximum as compared to tau max at C. So this is your final answer. So next topic, let's take next topic, that's said as hollow sections. Let's call it as hollow section. So you have this shaft, and after that it's in this fashion. So this part, your material is only available for this part only. So we call this one as hollow shaft, hollow circular shaft. So you have this, from the center you have some d outer, diameter outer, and you have some d inner also, inner diameter and outer diameter. This part is your solid part, and this part is your hollow. And we have defined one term, that's beta. That's the ratio of d inner by d outer, that is lesser than 1, d inner by d outer. Now you are applying a torque. Let's say you applied a torque T. There should be some resisting torque. So that resisting torque is contributed by so small dA and tau into R. So if I write that equation, I would say that equation would be equals to that torque, tau by R equals to tau max by J, tau by J. So you write the equation, and I would say that the thing is that so if I write the equation now, tau equals to t by j, tj by r, tau by r. Yeah, equation is wrong. Tau by r, t by j. So if I write the tau equals to tr by j, so you got this equation. Now we have different combinations. We have already shown you the variation of the shear stresses in this section. I said this is your section. I said this is your section, and this is your hollow section, and there is some material outside. The variation of the shear stresses. If you take this point, if you take this line, reference line, I would say the bending stress. I would say that shear stresses vary in this fashion, and similarly from this side, shear stresses vary in this fashion. So this is the shear stress variation, and there is some value of tau minimum, and there is some value of tau max and tau minimum. And similarly from this side, if you take, I would say this is your reference line. There is some value of tau max, and there is some value of tau max. There is some value of tau minimum. There is some value of tau minimum, and I have this variation. So this is tau variation in this hollow section. And I would say what should be the value of tau max? So if you go from the center to a value of r equals to r, capital R, and there you would get tau max. So if I substitute that value, that what should be the value of maximum torque? I would go that means you should go to the value of r and divided by j. The value of j, that's we can say that's the area, that is the polar moment of inertia for the part that is solid. For the part that is solid, that is equals to pi by 32, and d to the power 4, d outer to the power 4 minus you have to subtract the polar moment of inertia because of the hollow section. So that's minus d inner power 4. So you got this part. And similarly, if you write that what should be the value of tau minimum, and for the value of tau minimum, you have to go from the center to the value of y equals to that smaller r equals to d inner by 2. You have to go to the value of r equals to d, that r equals to di by 2. So that would give you tau minimum. Tau minimum at the rate of r equals to di by 2. That would be equals to similar fashion. That would be equals to t. Yeah, that would be equals to t. And small r, I would write d inner by 2 divided by pi by 32 and d 0 power 4, d inner power 4. So you got this tau minimum and you got the tau maximum. Now if you simplify it further, the value of r would be equals to d outer by 2. Now if you take that, I would write d outer by 2, or I can write 16 times d outer divided by d outer power 4, 1 minus d inner power 4 by d outer power 4. So you got this part. Now if I say this value would be equals to 16t by, and pi was also there, pi 16t by pi d outer cube 1 minus beta to the power 4. So I got this equation, final equation, that the tau max equals to 16t by pi d outer cube 1 minus beta power 4, where your value of beta was equals to d inner by d outer, and that's lesser than 1. So let's take the tau minimum value also. I would write that 16t d inner by pi, and you take the value of d inner common. You take this one as common. I would write d inner power 4, and you got this one, d outer by d inner power 4 minus 1, and you would get some value. You would get some value that would be equals to 16t by pi d inner cube divided by this one, value of this one would be equals to 1 by beta power 4 minus 1. So you got this part. Right. Further, if you simplify it, I would write 16t by pi d inner cube, and you have this. If you simplify it, it would be equals to 1 by beta power 4 minus 1. So that would be equals to 1 by 1 minus beta power 4 and beta power 4. So you got this one. That's your tau minimum. 16t by pi d cube 16t by pi d cube beta power 4 1 minus beta power 4. Now if we take some problems on this concept, let's say, let's take the problems. So you have that diameter, inner diameter is 0.7 times outer diameter for the shaft, and the shaft has to resist that, or we can say it has to transmit a force or a power of that. It has to transmit that 3500 kilowatt power. It has to transmit this amount of power from motor, I can say, from motor to some other part of the other machine, I can say. So it has to transmit this amount of power at the rate of 200 revolutions per minute. And see, we have not studied this part now. We have not studied this rotation. Yeah, let's have that rotation also. Let's keep the question as it is. So 200 rpm, and if the your tau max equals to 50 megapascal, maximum shear stress that can be allowed in the material, that should be equals to 50 megapascal. So you have this one. Say the question says I have a diameter 0.7 times d outer for the shaft. It has to transmit a power of this much at the rate of that rotational speed. I would say this is the revolutions per minute that shaft is rotating, revolving these 200 revolutions per minute. So you got this one. And maximum allowable shear stress equals to 50 megapascal, and you need to say what should be the diameter of the shaft. And after that, you have to get the value of maximum angle of twist also at the rate of tau max. So once you got the value of diameter, after that you say at this value of tau max, what should be the value of t? What should be the value of theta? So you have this one, that the shaft, it's connected to some, from this side it's connected to some motor. Some motor we have that. Let's say this is a motor. We have some motor here. And it's connected to the shaft is connected to the motor, and the motor is transferring some torque of T that was given to you in this problem, equals to 3500 kilowatts, and it's rotating now. It's rotating it in the form of, it's rotating with some angular, I would say, rotational speed of omega. So omega is your rotational speed. That's radian per second. And this is the length of that shaft. And here is one more member connected. Say some gear is connected, or some I would say generator is connected. Some sort of gear, I would say. There is some gear connected. So it would transfer that force to this gear now. That amount of torque would be transferred to this one, or that power would be delivered to that gear, and the gear would start to do its job then after that. So we have that. We say that the power. So we said that the power developed. We have that. We said that the power, how much power that transmitted, that is a function of what is the torque you applied at this shaft. What is the torque you applied on the shaft, and what is the omega on which it is rotating. So your rotational speed into torque, that's your power transmitted. So your power is a function of torque applied and the rotational speed of the shaft. So your torque, we know that torque is Newton meter, and omega is your radian per second. So finally you got the value of power equals to Newton meter per second, that's watts. So your P equals to T omega. So P equals to T omega. Where omega is your rotational speed. If you convert it into that, I would say that is 2 pi frequency, 2 pi nu, 2 pi f, where f is your frequency, number of cycles, number of revolutions per second, hertz. That's number of cycles per second. How much time is that a shaft is rotating per second? And if you convert that into per minute, if you convert it into RPM, number of revolutions per minute, I would say finally that power equals to torque times 2 pi n by 60, where n is your number of revolutions per minute. So final value that power equals to 2 pi nt by 60. 2 pi nt by 60. So let's have this final equation that power equals to 2 pi nt by 60. Now from the problem we had given that the omega, actually this is equals to, this is r, this is number of revolutions per minute. So you have given that n equals to number of revolutions per minute, that is n, 200 rpm. If you say what is the frequency, I would say this is number of revolutions per minute, and if you say divided by 60 per minute, we have some seconds, 60 seconds, so we'll get some value of 3.3 per second. So number of revolutions per second would be equals to 3.3, some sort of 3.3. So you got this one. So I would write the equation that power equals to torque into omega and 2 pi nt by 60. So you are provided with power. So from this power, if you substitute here, and n also you know, and you can get the value of t. And if you know the value of t and you use the torsion formula, tau by r, so you can get the value of r, or you can get the value of j. From that we have some value of diameter. So I have some value of diameter that we need to get. Tau we know, r we can also know, and j we can also know once we have this equation. So let's get the value of t first. Let's get the value of t. So I would write the equation P equals to, so I would write the power equals to 3500 into 10 to the power 3 watts. Watt, the unit of watt, that's Newton meter per second. So let's keep it in terms of Newton meter per second, and that should be equals to 2 pi nt by 60. That equals to 2 pi n and t by 60. That this part you have to keep in rpm. Because you are already divided by 60. So you have to keep it in the value in rpm. Okay, 200 by 60, and you have to multiply that t. So you get a value of t equals to that torque developed equals to, that comes out to be equals to 161.197 kilonewton meter. So you got some value of torque, and this torque, it has to be resisted by that shaft. So if I write that equation, you have that shaft, you have some d outer and d inner, and you are applying some torque tr. There's some tau max. Tau max would be equals to 16 t by pi. See for the tau max, if you say for the tau max, you have to keep the d outer cube 1 minus beta to the power 4. You have this equation. Now if I solve this equation now, I know the value of t, I know the value of tau max. That's provided in the question, that tau max is 50 megapascal. Now if I substitute those values, I write that 50 megapascal equals to 16 t. The value of t is here. The value of t equals to 161.197 into 10 to the power 6 Newton millimeter divided by pi. D, value of d, I don't know. There is some value of d outer. And 1 minus beta. What's the value of beta? It was given. The value of beta equals to d inner by d outer. That's 0.7. So 0.7 power 4. So I got this part. So I can get the value of diameter. Diameter is that you solve it, you get some value of answer, then you inverse, do 1 by 3 of that. So you got a value of d equals to 282 millimeter. So this is your outer diameter, outer diameter you got, that means inner diameter is also, you multiply that 0.7 times d outer. So you got the outer diameter. Now the next part of the problem is that you have to calculate theta also. You have to calculate what should be the maximum theta allowed at the rate of tau max. So if I write that theta maximum at the rate of tau max, that equals to tau by r, and this was your g theta by l. That means L goes upwards, so divided by G. So you got this equation. And value of tau was equals to maximum tau 50 megapascal, provided in the question. 50 megapascal. Length of L was equals to, the value of L was equals to, in the problem L was equals to 4 meter, and the value of G was equals to 80 gigapascal. So let's use those values. So L was equals to 4 meter divided by the value of R. Now we can take the value of R at the rate of tau max. At the rate of tau max, R equals to d outer by 2. Can we take that? At the value of R, at the value of tau max, we have R equals to d by 2. D outer by 2. That is 280 by 2. 282 by 2 millimeter. At the value of G was equals to 80 gigapascal. So you can get the value of theta maximum. So you got some value of 0.0177 radian, or you can convert it into degrees. That's 1.0159 degrees. Now let's have one more. Let's take one more problem. 1, 2, 3, 4. So the problem is that you have some motor, and it's connected to the shaft, or we can say shaft is connected to the motor. There is some support also here. So that after that we have some gear. Here installed. There might be some machine or device. So we have some gear. Let's call it as gear C, and we have one more gear that's called as gear B. So this is your B, and this is your A, point A, where your connection is. So the shaft, we say the shaft is your ABC. A shaft of ABC, the lengths are also provided. Lengths are your 1.1 meter and 1.2 meter. Now one more thing is that you have some shaft of steel, ABC. Diameter is 50 millimeter, and you rotate because that shaft rotates because of the motor. So there is some omega, and it's provided that the motor delivers 50 kilowatts. That motor delivers 50 kilowatts. It delivers 50 kilowatts, and that gets transmitted to the shaft. And once it reaches to the point B, it relieves that, how much amount? It relieves 30 kilowatts at B. So your gear B takes the 30 kilowatts. Your gear B takes 30 kilowatts out of those 50. Your gear B takes 30 kilowatts, and after that, at point C, gear C takes the resting of that 20 kilowatts. Rest of those 20 kilowatts. Now one more thing is that the omega, we have this omega, and the frequency equals to 10 hertz. Frequency is 10 hertz. And based on this problem, you have to say what should be the maximum shear stresses developed in the shaft. what should be the maximum shear stresses in the shaft? What should be the maximum shear stresses that have developed in the shaft? Any part of the shaft. So maximum shear stress we can calculate if we know that what is the maximum value of torque developed in the shaft. We have two parts. One is your AB, and next one is your BC. Once you get the value of T1 and T2, out of those T maximum would be there, and you can get the value of tau max. So also after that, you can solve for the theta angle of twist between A and C. From the side A we have that motor, and from the side C we have gear. So you can say theta A with respect to C, yeah, theta C with respect to A. Value of G equals to 80 gigapascal. So this is your problem that has been designed. So let's have that problem again. I would say your motor delivers 50 kilowatts to the shaft. Out of that 30 gets received by gear B and 20 gets received by gear C. And you want to say, based on this one, what should be the maximum shear stresses developed? And for that, you need to get what should be the maximum value of torque that's developed anywhere in the section. Because your cross section is same, that means the equation tau by R equals T by J. So we have only one variable, that's torque, and because of that we can get tau max. So we have that tau AB and tau BC. Because of that we have tau TAB and TBC. So once you go out of these, some value of tau would be maximum. So accordingly we can get tau T maximum. We have some value of tau maximum also. So we need to say, we need to convert that that power delivered in terms of torque, because from the torque delivered we can say we have that power delivered. So I would solve that. I would convert that torque. If you have 50 kilowatts, if you have 50 kilowatts power, if you have this 50 kilowatts power, that I can write Newton meter per second. This is your power, and that equals to some T, or the equation we know, 2 pi nt by 60, 2 pi nt by 60, 2 pi n and t by 60. So what is the value of n? That's revolutions per minute. But the data was provided in terms of that 10 hertz. It was given that that n equals to 10 hertz, but n should be in RPM. But it's already providing that frequency equals to 10 hertz. That means revolutions per second, RPS. So you don't need this 60. So you can write the equation that 2 pi f by 60. You can then write the equation in terms of 2 pi f by 60. So you can write the equation in terms of this one now. 2 pi f by 60. 2 pi f into t. 2 pi f into t. So you substitute the value that 2 pi into value of f is equals to t and into t. So f is your 10 by seconds, 10 per second, rp per second, revolutions per second. So forget about revolutions per, and your unit is rps, that is per second. So final value of torque would be equals to that, how much torque that has transmitted because of that motor towards shaft. That is equals to, you solve it and you get the value equals to, let's approximate it with it to value of 796 Newton meter. Let's approximate it to the value of 796 Newton meter. Now we can make that problem in this fashion. So you're applying a torque. Let's say you're applying a torque either anti-clockwise or clockwise. It's not of that issue here. So you apply some torque. Let's say the arrow is the clockwise direction. So you applied a torque of 796 Newton meter, and we have some point B, and we have one more point, that's C. So those 2 points take some amount of torque at B in the opposite direction. So this is your opposite direction, TB and TC. TB, TC. We have that. We can say out of that, the problem says that you deliver the power, you deliver some 50 kilowatts power, and 30 takes B, and 20 is taken by C gear. So if you take the percentage, or directly, or if you solve it in this fashion, that that torque developed at B, that equals to power received by B, they divided by 2 pi F. Similarly, torque at C equals to power delivered at C divided by 2 pi F. Value of PC, we can substitute a value of PC was 30 kilowatts, and this one is your 20 kilowatts, and accordingly you can get the value of torque B and torque C. Or in this other way, you can say, out of that 50 kilowatts, out of those 50 kilowatts, you can say 30 goes to the B, and 20 goes to the C. So this is your 60%, and this is your 40%. And you can say, if the amount of torque developed at the point of motor and shaft, that is 796, so it is 60% torque received by B, and it is 40% torque received by C. So this way, or the other way, you can solve. So finally you got that torque resisted by B, torque developed at B, and torque developed at C equals to 478. Let's approximate it to 478 Newton meter, and second one is at 318 Newton meter. These are your approximate values, 478 and 318. So this is your 478, and this is your 318. Now from this one, if you make the TMD, firstly you can say this is your line diagram. That thumb is, that's rotation. Rotation in this way, so thumb is outwards. So I would say this is your 796. After that, there is your 478, and this one is your 318. If you make the TMD, that would look like so. Or firstly, you can say, if you cut those sections, I would say you are applying at 796 here, and there would be some 796 here also just before. After that, you are applying some 796 in this fashion, and you are applying 478 in this fashion. So net value of 7, that 318 would be the difference of the two. So you have this value. If you make the TMD now, the TMD would look like, so yeah, you have negative 796. So it depends on the direction, that I assumed that you are applying a clockwise here. So 796, we have some 796 negative. After that, you are receiving in the same direction, so it would increase by amount such that net value would become 318. After that, a constant value. So both are negative. Had you applied that in the anti-clockwise, then the diagram would have been in this fashion, positive, both the values positive. So finally we can say, so the Tmax developed would be equals to, that's equals to 796 Newton meter. So the tau max would be equals to 16T by pi d cube, 16T by pi d cube, pi and d cube. Value of d equals to, what was the value of d? That value of d is equals to 50 millimeter. So 50 millimeter. So you got the tau max. Maximum shear stress is developed equals to 32.4 megapascal. 32.4 megapascal. And similarly, if you solve it for the tau, that was your for the part AB. If you solve it for the tau max in the part BC also, so that was equals to 13 megapascal. 13 megapascal. And one more thing is that you need to get the value of theta. We can also solve that theta also. So because of the torque developed in the first part, let's say these are your two sections. Let's say this is ABC. So I would write theta in the AB. What's the value of theta in the AB? Theta in the AB would be equals to some torque. Let's forget the sign, because we have both the signs. We have both the torques as negative. Let's forget the signs. I would write torque that theta developed in the AB, that would be equals to torque TL by GG. TL, the value of L was equals to 1 meter. TL by GJ, value of G was equals to 80 gigapascal. So 80 gigapascal, and value of j was equals to pi by 64 and 50 power 4 millimeter power 4. So you got the value of theta a b, that equals to 0.0162 radian. And similarly, you can solve theta b c, that equals to some torque of 318, some torque of 318 Newton meter. Length was equals to that 1.2 meter. So 1.2 meter. TL by GJ 80 gigapascal, and J was equals to pi by 64, pi by 32. J is equals to pi by 32. Yeah, this is pi by 32, and 50 power 4 power 4, and you got a value of theta BC equals to 0.0078 radian. And if you solve for the total theta between A and C, the question was saying get the value of theta between A and C, that is theta AC, that equals to theta AB plus theta BC, that is equals to sum up those two, and you got the value of theta total equals to 0.0240 radian. And let's take the third problem of this kind. Let's take the third problem of this kind. So we have one more that's saying there is a spout and there's some shaft. Attached here. After that it goes there's one more shaft of decreasing dia. So there is a dia that's and you apply the torque of 250 Newton meter here. The two arrows represent the direction of thumb. That is the direction of thumb. That means the clockwise torque has been developed at this point, 250. So that's also in this way I can say that's clockwise torque 250. So this point is A, this is B, this is C, this is D, and we said that one thing for the part DC, we have drilled a hole. For the part DC, we have drilled a hole of diameter phi equals to 44. If the total is 60, if the total diameter is 60, we have drilled a hole of 44 millimeter. That means the rest part would become 16. So the thickness would remain 8. 60 minus 44, that is 16. So some sort of this fashion. So the material that remains is this part only. So this is the material that is remaining. So this material is there only available now. So this is the material, and you have drilled a hole here. So this is the hole that you have drilled. That this is your hole drilled. That means this part, DC part, would look like a hollow section of thickness. I would say thickness is equals to 8. This is also 8, and the hole is equals to 44, such that total value of 60 is there. So this part is your hollow section. This is your DC. Now the thing is that you are applying one more torque at the junction of B. That is equals to some torque of that's equals to 2000 Newton meter. And value of G for the steel is equals to 77 gigapascal. Angle of twist, you need to say what is the angle of twist at the end A. Angle of twist at the point A, at the free end, I would say, at the A. That's your point A on the free side. So what we can do, we can say what should be the free body diagram look like. So you need to make the free body diagrams, and after that you can also show the line diagrams also. Let's make the line diagram first. If this is your 250 and this is your 2000, there is only one support that is going to resist it. That should be equals to 225 2250. That should be this one. Torque developed at D. That should be 2250. And if you take any section now, if you take DC now, if you take DC, I would say there is a torque of 250 in this fashion, 2250 in this fashion, and there will be some balancing 2250. And similarly now, if you take CB, this is your DC, this is your CB, and there is some torque of 2250, and there would be some and you just cut just before B, and there would be 2250 also here. After that, you have smaller shaft diameter, and you apply 2250 in this direction, and you have opposite 2000. That means net value would be in this fashion 250. So you got the free body diagrams. That means you got the different moments. So now you have to make the torsional moment diagram. So this is your reference line. I would say you are going in the same direction. Your moment is in the same direction. Torque is in the same direction of your traverse. So a positive 2250, positive value. Let's say this is 2250. After that, it remains constant to the point DC. After that, this is also constant for the up to this point CB. After that, you have AB. There is a decrease by an amount of, because there is a decrease of 2000. So net value would go down, and finally you have a value of 250. After that, it would remain constant in this part. Once it reaches 250, it would go down. This is your positive TMD. 2250 and 250. Now you got the equation. You got the equation. You have this. What you need to get? You need to get the value of theta A. You need to get the value of theta A. I would say that theta A would be equal to theta at A with respect to the D support. That is theta A minus theta D. That is 0 theta A. So I would write theta A with respect to B plus theta B with respect to C plus theta. I would say theta C with respect to D. Or we can say theta AB plus theta BC plus theta CD. Now you need to solve this when you have the equation TL by GJ. TL by GJ, your different torques are applied on the different cross sections. So your T is different, L is different. So value of L I would solve here. I would take the value of L here. Let's say this L, this one is your length of 0.6 meter. And this part is your length of 0.2 meter. This is your 0.2 meter. And this part is your 0.4 meter. This is your 0.24 meter. So I would write theta AB, that's this part. Here the torque is equals to 250. Torque here is 250. Let's write theta AB equals to 250. I think we should zoom in. So let's write here theta AB. Theta AB is 250 Newton meter. L, the value of L for the AB part is equals to 0.4 meter. 0.4 meter. TL by GJ. Value of G is constant. Let's keep the value of G outside. That is 77 gigapascal. This is your value of G. That's constant for every term. And we have this part also, pi base 632 also. We can keep that also outside. So value of J would be pi by 4, pi by 64, and diameter here. Diameter here would be equals to, I have not given you the diameter here. The diameter here would be equals to, I would write diameter for the AB, that equals to 30 millimeter. This is 30 millimeter. Here the diameter is 60. Diameter for the BC is 60. And for this part, we have that hollow section 60. 30, 60. Okay, 30, 60. So I would write pi by 32 and 30 to the power 4 millimeter power 4. So this is your first part. This is your first term. And I would write plus theta BC. For the BC, you have a torque of 2250 Newton meter, and length of, what is the length between CB, that is 0.2 meter. That is 0.2 meter. TL by G. G I have kept outside, and J pi by 32 we have outside kept that. We have kept that outside, pi by 32, and left we have the diameter of 60. That's 60 to the power 4 millimeter to the power 4. Plus for the part AB, we have hollow section. We have the hollow section. That is 60 minus, what is the inner diameter? If I have this hollow section, what is the inner diameter? Outside diameter, we can say d outer would be equals to 60, and d inner equals to 44, 60 and 44, and a torque of 2250. So I would write 2250 Newton meter, and the length L 0.6 meter by GJ, that is pi by 32, and d outer minus d inner, power 4 millimeter power 4. And finally you solve this equation. So you got this equation, and you can finally have the value of theta at free end, that is equals to 0.0403 radian, and if you convert it into degrees, you could get a value of 2.31 degrees. That's in this way 0.0403 into pi into 180 divided by pi. So you got this one. Now if you want to take one more problem, that is a problem that says we have a shaft parallel combination. So I would say that is shafts in series. So the topic for this one is shafts in series, shafts in parallel. So we have parallel combination, that this is your fixed side, and you have a shaft. I would say this is a tube. You have a tube. Let's say this is your tube. Let's say this is your tube, and I call it as aluminum tube. It's made of aluminum tube. So the tube thickness is equals to 8 millimeter. This is 8 millimeter. Thickness of 8 millimeter. Let's say this is aluminum. And from the bottom also, this is aluminum. And inside we have kept a steel rod, or we can say steel shaft. So we have some steel shaft, but the thing is that there is a rigid disc between the two. On this side we have attached a disc. We call it as a rigid disc to ensure compatibility, to ensure that what we call as composite action, that is strain compatibility, ensures composite action. But the cross section looks like somewhat in this fashion. So you had this thickness, you had this tube of aluminum, After that, the entire diameter is not taken by the steel. There is some gap between the two. So there is some steel shaft. This is some solid steel shaft. And this is aluminum. There's a gap. I would say there is a gap between the two. There is a gap. I would say G. There is some gap G. So gap of G equals to, that gap equals to 5 millimeter. So net gap of 2G equals 10 millimeter. If I take the entire diameter, of the composite section, I would say entire section is equals to 76 millimeter. And out of that, we had the thickness of tube that was given to you 8 millimeter. This was your 8 millimeter. This is also 8 millimeter. And if I write that that diameter of steel would be equals to 50 millimeter. If I write 8 plus 5 plus 50 plus 5 plus 8, that is 76 millimeter. So the configuration looks like in this fashion. And to ensure that composite action, we have attached it at a rigid disk. We call it as rigid disk here. Okay, so ensure that compatibility. Now the length is provided. Is the length provided? And problem says that you want to say what should be the maximum torque applied. How much maximum torque you can apply? Maximum torque applied. How much you can apply? Torque maximum, Tmax. Because for the condition that we have maximum shear stress applied, allowed in the steel equals to the maximum shear stress you can allow for the steel is 250 megapascal, and maximum shear stress you can allow for the aluminum tube that equals to 70 megapascal. And one more thing is that the value of G for the steel and G for the aluminum equals to, this one is your 77 gigapascal, this is your 27 gigapascal. Okay, so you need to get the value of Tmax. So for the shafts in parallel, if you have shafts in the parallel, you have 1 and 2. I say that you apply a torque of T. Now you apply the torque of T. The question is saying how much T you can apply, how much Tmax you can apply. So you apply the torque of T. We say that we have the compatibility that theta in the 1 is equals to theta in the 2, because both will have the composite action. So there is a strain compatibility. If one gets rotated by theta, next one would also get some same amount of angle of twist theta. So I would say theta 1 is equals to theta 2, and this is your condition, that compatibility condition in the strain in the composite bars, composite shafts. Theta 1 would be equals to theta 2, and accordingly I would get the value of T1 L by Gj. The length is same for the two materials. L is same. So I write T1 L by G1 J1, that is T2 L by G2 J2. So I know the G2 and J2. I can get the value of T1 and T2. So finally I would say in the parallel combination, that total torque is resisted by material 1 and material 2. So there is this equation we have, and there is one more equation, that is T1 by G1 J1, that's T2 by J2 G2. And L is same, that gets cancelled, this is theta. So based on these two equations, we can get the value of T1 and T2. So once you got the value of T1 and T2, you can say what is the total that you can have, T1 plus T2. Okay, so let's solve this problem. I would say that theta in the steel, that is equals to theta in the aluminum. So that would be equals to theta steel, that torque in the steel, length is same for the two, and divided by G for the steel. Let's write that as 77 into what should be the value of polar moment of inertia for the steel. For the steel, we have diameter of 50. We have diameter of 50. So I would write that pi by 32, 50 to the power 4 millimeter power 4, and that should be equals to would be equals to T in the aluminum, TA, and L is same, and you have that 27 gigapascal into the value of J for the aluminum is in the form of hollow tube. So we have some D outer and we have some D inner also. So if we take from the center, you have some, I would say D outer would be equals to 76, and we have some D inner also. There is some D inner also. This is your D inner from this part to this part. So I would say that D inner is equals to 76 minus 8 minus 8. That twice thickness you had to subtract. So you got a value of 60 millimeter. So you have the 60 and 76. 60, 76. Pi by 32, 76 power 4 minus 60 power 4 millimeter power 4. So you get this equation, and you can say that TS is equals to TA, and we have some factor here, and it says that TA equals to 1.144 TS. So you got this part, that torque taken by aluminum shaft, hollow shaft, that's 1.144 times that TS. And we have one more equation that TA plus TS equals to TA plus TS equals to T. TA plus TS equals to T, and you use that equation also. So I would write 1.144 TS plus TS, that is T. So TS equals to 0.467 T, and T next one is that TA, that is 0.533 T. So this T, so we have got these two values, and we don't know what's the value of T itself. What is the value of T itself? How can you get the value of T if you don't know the value of T? How can you get the value of TS? So one more thing is provided to you. This part we have not touched it yet. Let's touch it. So I have touched it. So tau max in the steel, it's saying that the maximum shear stress you can allow in the steel, that would be equals to T in the steel, TR by tau by R, TR by J in the steel. Isn't it this equation? And for the solid steel section, we can write the equation T 16TS by pi d cube. Can I write this equation? If I solve it, I can get the value of TS, and thereafter I can get the value of T. I can get the value of T. If I write this equation, if I solve it, I would say your value of 16 into TS. I don't know the value of TS, but I do know the value of TD, that diameter of the steel. Diameter of the steel is 50 millimeter. 50 millimeter. And that I have to equate it with the allowable shear stresses in the steel, that's 120. That's 120 megapascal. So I can get the value of that torque in the steel developed. Torque in the steel that has developed, that is equal to 6.31 kilonewton meter. And similarly, you got this value of TS. And if you want to say how much torque you can allow, you got this value of TS. And similarly, based on this, you can get the value of T. So that TS, that based on this one, you can get the value of T. That would be equals to 6.31 kilonewton meter divided by 0.467. So you get a value of T that is equals to, yeah, actually you got some value. So you got some value of some value of 6.31 is the final value. So you got some value of A, let's call it as value of Z. So you got some value of Z, and you divide it by some 0.467, and you get a final value of 6.31 kilonewton meter torque. So this is your first condition of torque. And if you use the second condition for torque, that TA equals to 0.533, and for that, if you use that in the equation for the tau max in the aluminum, if you write this part now, if you write tau max in the aluminum, that's equals to 16T in the aluminum by pi d cube. But for the aluminum, you have a shaft, hollow shaft. So you write, for the maximum, you write d outer power 4, d outer cube 1 minus beta to the power 4. What is the value of beta? Can you tell me what is the value of beta? The value of beta would be equals to 60 by 76. 60 by 76 power 4. And from this one, now if you substitute the value of TA, the value of TA equals to 0.533T, that is 0.533T. If you substitute 0, that is 0.533T, and you can get the value of T. And next T, you equate it with that shear stresses allowable in the aluminum, that is 70 megapascal, and total value is equals to 70 megapascal, and you can get the value of T, that equals to 6.92 kilonewton meter. So finally, you got two different values of torque, and the problem says that how much torque you can apply that should be safe. See, if you apply this amount of torque, your aluminum would be safe. It's already safe. Now, but if you apply this amount of torque, 6.92, that means the torque developed, that maximum torque your steel can have at tau max, that's 6.31 only. So if you apply that 6.92, that means the stresses in the steel would be greater than tau max. That means the stress is developed 6.92. If I have that equation that tau developed in the steel, that is equals to 16 times, if I substitute the value of Ts as a value of that, if I substitute here the value, final value that that we have equation in this format, then value would be here more than that as compared to that Ts. So this would be actually 1.144 Ts that we have here actually. So you can get the value of tau in the steel that is more than tau max. So your material will fail. That means your shaft of steel would fail. So you need to ensure that both materials are safe. That means you should out of those two values of T should take the minimum value. That is 6.31 kilonewton meter. So this is the safe value of torque that you can apply on this cross composite section. So finally you had this composite section, and you had the steel, and how much torque you can apply, that is safe. That should be minimum of those two, such that both materials are having stresses lesser than the tau max values. Hope you enjoyed this problem. And this is the end. I think this is the end of this chapter. I think this is the end of this lecture. Thank you for watching this series of strength of materials. Thank you.